So, the talk is meant as an introduction to my subject, which is Borel Combinatorics. It's okay if you don't know what any of those words mean. I will in fact give you a definition of Borel which doesn't require any topology. But before I do that, let me just state the sort of main theme. And the main theme is we want to color certain graphs, in this case infinite graphs. Okay, that's the algorithms question, right? Given a graph, can I color it? The mathematician's question is actually how to disprove that you can color this graph. So I will start the talk with two examples. One where you can in fact algorithmically color this graph, and one where you cannot. And then I'll give a formal definition of what I mean by algorithm, or algorithmically color. So to start off, we start off with the vertex set of R. Okay? So every real number is one node in this graph. And all the edges are just connections between one number and then its increment. Okay? So for instance, -1 should be connected to -2 and so forth. What are the connected components of this graph? Sure, but each connected component looks like what? I may also refer to a connected component as a comp. Okay, for short. Each connected component looks like this thing. Note that this is in fact a tree. Okay, it's a very degenerate tree, maybe a bamboo tree, but it's still a tree, and so it does fit the theme of the talk, which is arboreal Borel combinatorics. How do I color this graph in such a way that it is proper? In other words, each vertex should be a different color than its neighbors. Well, here's one such coloring. So I color a vertex red if the floor of that number is even. For instance, I color this entire segment red. I color this entire segment red. And I color this entire segment red. And similarly, if the floor is odd, okay, I color it blue. And hopefully you believe me that this in fact is a proper two-coloring of this graph. In fact, it's very algorithmic. In fact, I've given you the algorithm. Now, in contrast, consider this graph. Okay, the vertices are the circle. Okay, so every point of the circle is a vertex in this graph, and the edges, much like this, are a vertex here connected with some vertex that is an alpha rotation away. Some alpha. Okay, maybe it's 2 pi alpha, but I don't really care. All right. And let's specify that alpha is irrational, so that this thing never loops back on itself. That is left as an exercise for you. What are the connected components of this?
Bamboo trees.
Yes, exactly the same bamboo trees as before, in fact. And so if this is two-colorable, okay, then this should also be two-colorable, because each connected component looks like this. And I can color each connected component with 2 colors. So actually, let me define something. The chromatic number of a graph, okay, the graph G, is the minimum number of colors needed in a proper coloring. Where again, proper means that adjacent vertices do not share the same color. Okay. Well, it turns out, and I will prove this for you, assuming the black box of Lebesgue measure theory, that you cannot color this with 2 colors. Okay. However, you can color it with 3 colors. And in fact, you can use as little of the third color as you want. Okay. So for instance, if my third color is yellow, I can color this extremely small interval yellow. And then I'll define the rest of the coloring in this way. Okay. In formulas, it's every, well, okay, let me describe it in pictures first. You have this yellow interval, and then I rotate that whole interval by an alpha rotation. Okay. And then I color that thing blue. And I rotate this whole interval by an alpha rotation, and I color that red. And I rotate this one by another alpha rotation. Okay, fine. There's an overlap here. That's a little dangerous, but I can just color the part that's not yet been colored blue. Okay. The mathematical formula describing what I just said is here. And again, I will leave it as a small exercise for you to determine that, in fact, this must be proper. Are there questions about the setup of these two examples? Yes, please.
So it's like the nicest interpretation of the, like, all the connected components for this circular graph. Like we have like Armazzi for the straight line.
In fact, I cannot describe them for you,
Okay.
which is what I was about to prove. But the thing I do want to point out is that each connected component is identical. Okay?
Yeah.
So if you're only looking at one connected component at a time, you cannot tell the difference between this graph and this graph. But somehow in aggregate, all of them together, you cannot color them in a certain way.
Thanks.
Before I, okay, never mind. Let me define for you what I mean by algorithmic coloring. Okay. This is a little strange definition, but I have drawn some pictures for you, or actually, my friend Hunter has drawn some pictures for us. Okay, so let me just read it. A countable Boolean pseudocircuit, okay, is a directed graph on a countable vertex set, V, which is split into two disjoint sets, one set of input gates and one set of logic gates. Okay. The in degree of any input is 0. So for these input gates, there's nothing being fed in. Okay. But for all the other logic gates, which are labeled one of these three symbols, and, or not, those guys might have things connecting into them. Okay. So for example, let's start with this picture. Okay. If I have countably many inputs, okay, for example, if I have 0, 0, 0, where's my chalk? Then the and of two zeros is a 0. The and of these two zeros is also a 0. And you'll eventually see that they're all zeros. And so the infinite disjunction, or of all of these zeros, is also 0. Okay. So this is an example of a countable Boolean circuit. Okay. I will define an evaluation of the circuit on a certain input x as a function which assigns to every gate the value 0 or 1, where I have the requirement that on the input gates, it should agree with the input that I stated. Okay. And for each logic gate, it should be consistent with the logic of that gate. For example, here, I have the input 1, 1, 1, 1 ad infinitum. And I claim that there are actually two evaluations of this circuit on this input. One evaluation is if I put all zeros here. Okay. This is logically consistent with the logic of each gate, because this guy sees a 1, or takes in a 1 and a 0. And as an and of a 0 and a 1 is a 0. Okay. And in fact, all of them look the same, because they're literally the same. So that is one valid evaluation of this countable Boolean circuit, sorry, pseudo circuit. This one is another valid evaluation, okay, where each gate locally sees a 1 and a 1, and being an AND gate naturally outputs a 1. Any questions about this notion? Okay, great. So here, there were two possible evaluations. The ones with all zeros or the ones with all ones. In this example, okay, I claim that actually there are no evaluations. Okay. And this is because if this one is a 0, let's say, then 0, 1, and 1 have to AND to a 0. But a negation of a 0 is a 1. But this being an AND of a 1 and a, sorry, wait. I misdrew this graph. Very unfortunate. Unfortunately, I cannot fix my mistake on the fly. But exercise for you, there is a graph that looks a lot like this, that is not this one, in which you can detect this error.
I don't understand. What's the issue?
The issue is that in a correctly designed version of this, I would have a 0 somewhere. Okay. Actually, maybe I have a correct copy somewhere. Ah, yes, this is missing this arrow. My apologies. Okay, here's finally a contradiction. Okay. There is a 1 here, and there is a 1 here, but this is a 0. Okay, so this contradicts the logic of this AND gate.
Why is there not a contradiction before?
If I had instead chosen a 1 here,
All right.
then this would have been a 1 because it's a 1, 1, 1, and this would have been a 0. And again, there's a contradiction. A 0 and a 1 cannot produce a 1. Okay. So this situation has no evaluation. But the issue is here there's a cycle, okay? And here there's an infinite chain going backwards. Okay? And so if I just define a circuit to be something that doesn't have either of these problems, then in fact my assertion is that a well-founded pseudocircuit, which is one in which neither of these two things happen.
Why wouldn't there have been a contradiction even without that error?
I'll leave it as an exercise. Okay. In fact, there exists a unique evaluation. And I define the value of the circuit to be what the evaluation function says at the output gate. Okay. So for example, this circuit, I want to ask the audience, what values of x would make this circuit output a 1? Make this output a 1.
Sure. So is X just one thing, or is it all of them?
Well, x is a sequence of 0 and 1 you can put in at every input. And so,
And there's an and everywhere, right?
and here on the second layer, and an or on the third layer.
Okay.
Sure.
You need x not to be 1,
Yes.
and then a 1 somewhere else.
Exactly. Exists in I non-zero such that xi is also equal to 1. Okay. What about for this one? What about for this one? What are the x's that produce the output 1?
You need 2 1s next to each other? Oh, no, there's a thing at the end. I
Yeah,
missed that.
there's a negation at the end. And so in fact, it's the opposite of what you said. There are no 2 consecutive 1s. Okay. And just to emphasize, this is a valid Boolean, countable Boolean circuit. I said that there cannot be an infinite chain of things going backwards, but you are allowed arbitrarily long chains of finite things going backwards. Okay. And I'll leave it as an exercise to figure out what the correct x's here are. Okay. The whole point of that was to sort of, okay, actually, the whole point was actually this. I'll define a subset of 2 to the n, which is all the infinite binary sequences, okay, is called countable circuit computable, CCC, if there exists a countable Boolean circuit, well-founded pseudocircuit, such that it computes the indicator function of A. Okay. In English, A is CCC if you can compute in this sort of exaggerated, purely mathematical scenario, if a given element x is inside of A. Okay. So the whole point of that was to justify the philosophy that I can sort of give you a notion of algorithmically computable things. Okay. And then the definition of Borel that I'll give is the following. Definition, sorry, assertion. A subset of 2 to the n, is CCC, if and only if it is Borel, in the standard topological sense that you may be used to. Okay.
Sorry, what does that mean?
If you don't know what Borel is, take this to be the definition of Borel.
Okay.
So Borel is just something that is computable, for which you can compute whether an element is inside or outside of the set.
Okay.
And so the subject of Borel combinatorics is doing combinatorics, but things that are computable. Okay. Can you describe a computable coloring of a certain thing? Can you describe a computable matching of a certain graph? Okay, returning to this, the theorem that I'm about to claim is that there is no Borel two-coloring of this graph. Okay, there is no Borel two-coloring. And I will prove this using the black box of Lebesgue measure theory. So, I'll erase this. erase this slide. Okay, so assume that, in fact, I can break the circle apart into a red set and a blue set. Okay, and this is a proper 2 coloring of this graph. Well, observe the following fact. I claim that R plus alpha is equal to B. Okay. This should be quite intuitive. If I rotate the red set by an angle of alpha, okay, or I use the addition alpha here as an angle parameter, okay. If I rotate the red set by an angle of alpha, it must be the blue set. Okay. And in fact, it is an exact equality. And assume that these sets are Borel, so computable in some sense, in that sense. By the machinery of Lebesgue measure theory, okay, it must be then that the measure of these 2 sets is exactly the half of the measure of the whole thing. Okay. And so if I normalize the measure of the circle to be 1, then the measure of these 2 sets is a half. Okay. The Lebesgue density theorem, says that for a positive measure set, in fact, there are lots of points in it, so that if I get really close to it, and in fact, every interval containing that point will be 99% made of that set. So in this case, if I have a red set, okay, and this point is in the red set, or sort of a generic point in the red set, in fact, all of these intervals will be 99% red. Okay, will be 99% red. Okay, fine. But now, what if I rotate this interval, okay, by alpha? If I rotate this interval by alpha, then I will get an interval which is 99% blue. And if I rotate this guy by 2 alpha, I will get something that remains 99% blue. And as I rotate this 99% blue guy around, eventually it will overlap with this interval here. But every interval here that contains this red point was 99% red. And something cannot be both 99% red and 99% blue. This is impossible. And so in fact, using the machinery of measure theory, I have proven for you that there is not a Borel 2 coloring. So using measure theory, which will not feature again. Okay, I'm just telling you that this black box exists. I can in fact show that there does not exist a measurable 2 coloring. Because the same proof holds if I assume these are measurable, Lebesgue measurable, instead of just Borel. Okay. So we have this hierarchy of regularity. Okay. So we have Borel things which are the nicest. These are nice. We have measurable things which are slightly less nice. And then we have arbitrary, which are the worst of them all. And so these each have a notion of chromatic number. Chi b is the minimum number of colors needed to get a Borel coloring. Chi mu is the minimum number to get a measurable coloring. And chi in general, the one I had before, is the minimum color needed, in general. Yes, please.
Wait, really fast, just to make sure I understand. So by 99% red, do you mean like the blue is measure 0?
No, I mean the blue is like measure epsilon.
Oh, okay.
Yeah. We cannot get 100%. Unfortunately,
Yes,
Lebesgue
yes.
density does not allow us that. But 99% is enough for this.
So we're saying Lebesgue density theorem gives us some interval, some with 99% red.
Yeah,
Okay.
Gives us some interval where in fact every interval inside of it which contains that one point is also 99% red. Yeah.
Silly question. So that's 99% red. When you go alpha, then it becomes 99% blue. Then should you alternate or should you not?
Well, now I rotate by 2 alpha.
Oh, 2 alpha. Okay.
And then if I keep rotating by 2 alpha, which still is dense on the circle, okay,
Ah, okay.
then eventually I'll get something that overlaps with the original one. Okay, anyways, Borel is the nicest, measurable is the less nice, and arbitrary is the worst. And so you need a higher number of Borel color than you do need. So because things go this way, the inequalities go this way. Okay. All right. And I already found a 3 coloring of this graph using 3 colors. And so in fact, we have found that the Borel chromatic number, and in fact the measurable chromatic number of this circle graph, this flower graph, is precisely 0.3. So maybe that was a little interesting. But now I will say that I don't want to use this black box of measure theory. Okay, yeah.
Sorry, one more quick question. Does that flower graph have an arbitrary to coloring? By just sort of like
Yes.
naively coloring
Yeah.
every...
Yes, in fact, this is related to your talk. What I do is I have continuum many connected components.
Oh.
And I just choose a starting point on each one using the axiom of choice.
Yeah.
And that allows me to start with that one as red and then branch outward, just like I did with this graph that I've erased. And so using the axiom of choice, you can color it with two colors.
Cool.
But, you know, this talk is an antidote to your
Yes,
talk,
yes.
right? I'm trying to avoid the axiom of choice in a very, in this way. So, the second chapter of my talk will be giving you a problem in which the measure theory approach does not help. Okay, cannot get us all the way. Cannot get us all the way. All right. Let's see. Okay. So I'll have to let me give some comments on this. So I've defined a Borel subset of 2 to the n. Okay. But in fact, I can define a Borel subset of a lot of other things too. For example, I can define a Borel subset of R by having these sets, B1, B2, be an enumeration of the countable basis, B, Q, 1 over n, or Q in rational numbers and n in positive naturals. Okay. So this is an enumeration of this. Then for every x in the real numbers, I can cook up what's called a code, which is just 1 if x is in B1, 1 if x is in B2, and so forth. And this is something in 2 to the n. Okay. And if a subset of R is Borel, or countable circuit computable, if and only if I can turn my real numbers into these codes and then compute on those codes. Okay. So from now on, I will be working with a different space than R and 2 to the n. But rest assured, I can do exactly the same sort of thing. And I will also have a notion of Borel, or CCC. So, this is chapter 2. Let me start with what I mean by a Borel graph. A Borel graph is a V, which is a Borel subset of 2 to the n, R, or what's called bare space, which are, instead of infinite sequences of zeros and ones, it's infinite sequences of natural numbers. Okay. Okay. And edges, I will think about as a function from V cross V to 0, 1. And I want this function to be Borel. In other words, computable. In other words, if you give me 2 codes of vertices, okay, one sequence here, one sequence here, then I should have some sort of countable Boolean circuit that computes and spits out 1 if these 2 vertices are connected, or 0 if they're not connected. Okay. So this is a notion of a Borel graph. In other words, the vertices are computable and the edges are also computable. I'll now make this following assertion. If G has max degree D, less than or equal to D, which is a natural number. In other words, every vertex has at most D neighbors. Okay. D neighbors. Okay. Then it is a theorem that the Borel chromatic number of G is less than D plus 1. Okay, so less than D plus 1. I will not be able to prove this, but the proof is not terribly difficult. It's not terribly difficult. All right. Okay, very good. I will now define for you a graph. Oh well, actually, before I do that, this bound is actually sharp. Okay, and why is this bound sharp? It's because if I have kd plus 1, the complete graph on d plus 1 vertices, in other words, one vertex d here, and everybody here is also connected to everybody everywhere else, okay, then in fact I need d plus 1 colors. Okay, so maybe I'll start with a smaller graph. This is K4. I have 4 vertices, and every vertex is connected to every other vertex. And I need 4 colors for this. I need 4 colors for this. Because each vertex is connected to every other vertex. And so this is what's called a 3 regular graph, because each vertex has exactly 3 neighbors. And so if G contains kd plus 1, then chi b equals to d plus 1. So it's sharp. Okay, it's sharp. There is a theorem, again I will assert. If G has no copies of kd plus 1, then the measurable chromatic number of G is bounded by D. Okay, it's bounded by D. And this is where the graph I'm about to define comes in. So I will define a Borel forest, by which I mean every connected component is a tree. Okay. In particular, all the connected components do not have copies of kd plus 1 because they are trees. Okay. And trees do not have copies of kd plus 1. In fact, they do not even have copies of k3, okay, which is a triangle. So definitely no kd plus 1s. In particular, this theorem applies and says that the measurable chromatic number of this graph, the Borel forest, is actually less than or equal to D. But I will define for you a Borel forest which has chromatic Borel number equal to D plus 1. So this graph will have maximal Borel chromatic number, and guaranteed the measurable, measure theory will not be able to help us prove this, because measure theory only gets us up to D, okay, and not to D plus 1. Okay, so bear with me. In fact, I will define a D-regular forest. Or again, that means each vertex has exactly D neighbors. So let me denote by YD the D-regular tree. Okay. This is a countable object, and so extremely computable. Okay. This is not to be worried about. This is not the thing that is not the main character of this theorem. Okay. And that it's rooted. Okay. I'll define for you X, which is the colorings of this tree with natural numbers. Okay. So this is how I want you to think about it. Imagine I have this D-regular tree on the floor in front of me. I'll draw you an example for D is equal to 3. This is the root. I have 3 vertices here. I have 3 neighbors here, 3 neighbors here, 3 neighbors here, 3 neighbors here, and so forth. That is what this YD looks like for D is equal to 3. Imagine this tree laid out on the ground in front of me. And each spot on the ground is colored a certain color. Okay, so I'm standing on red, in front of me is blue, over here is green, and so forth. Okay, and there are countably many colors I can choose from. An element X in here is a coloring of this thing. Okay? And in fact, it's a coloring from this rooted vantage point. So I'm going to call these things views. Okay. So this is a certain view. In particular, if I walk along this tree, I will see something different. Okay. If I was at red before and in front of me is blue, then if I walk along this tree, then below me will be blue and behind me will be red. Okay. So the view has changed. Okay. You can also think about them as sort of heights. Okay, so if I have YD on the ground in front of me, then this is a height 1 bump, and over here it's a height 2 bump, and so forth. And so it's like an actual landscape that you can see. All right. And what are the edges? Okay, so these are the vertices, it turns out. And the edges are exactly the views that I see as I walk around on the graph. Okay. So the edges, these are called adjacent views. Okay. More precisely, I have a function fi from x to x, which takes in a view x and outputs the view I see when I walk the ith edge. Okay. The edges here are labeled, let's say by 1, 2, 3, in, let's say, clockwise orientation. So 1, 2, 3 here, 1, 2, 3, 2, 3, 1, and so forth. So all the labels of each edge is completely determined. No controversy here. And the view I see here, x, will be adjacent to, in this graph, the view I see after I walk the ith edge. Are there any questions about this very strange graph?
Yeah, so is it derived from a single coloring of this whole thing, and it's like all the set of views from one coloring?
No. That would be one connected component of this graph. Okay. But there are other connected components that I could never get to by walking around on the one I have now. In fact, there are continuum many connecting components of this graph. So again, it's a little weird. The tree I've drawn here is not the Borel forest in question. Okay. This is just the ground. The Borel forest in question are things like x is connected to fi of x. Okay. And that's connected to fi minus 1 x and so forth. Okay. So little strange. Okay. All right. What do I want to prove about this graph? Well, first of all, it is in fact deregular because I have exactly d neighbors for every view I have. Yes,
Wait, sorry, one more quick question. So, is it true that two views are adjacent, if and only if they both sort of came from a coloring of yd, and then you picked a root and that gave you one, then you picked a different root and that gave you the other?
Yes, by
Okay.
definition.
Yes.
Right.
Okay.
Good question. Any other questions about this definition? This is the main star of the show, so please ask if you have questions about this graph. This graph is, I assert, deregular. Okay. You have exactly d neighbors coming from all the views you get as you walk along the d paths here, d edges here. However, it's not a forest, okay, because there are cycles. In particular, if a certain coloring is periodic, okay, then I can walk around and end up seeing exactly the same coloring that I thought I used to see. So let me call this guy G. G is equal to G dot, disjoint union G circle, where these are the components, the comps, that are trees, and these are the comps that have cycles. And so it's actually not G that is the Borel forest in question, it is G dot. Okay, so I have actually finally told you Marx's forest. Okay, so this theorem was proved by Marx, a professor here at UCLA in 2016. All right. All right. Well, what do I want to show about G dot? What do I want to show about G dot? I want to show that the Borel chromatic number of G dot must be strictly bigger than D. In particular, that would force it to be D plus 1, because I have already stated the theorem that all colors of max degree D graphs are bounded by D plus 1. So what does that mean? That means that for all Borel, in other words, computable colorings F, from V G dot to 1 through D, okay, I think of these as a sort of scoring of the view. Okay. So remember, guys in here, are these x's, okay, and x dot is a view. And so f dot will score the view with a score from 1 to d. Okay, so you can think of me as standing on this graph, and in my head there's a countable Boolean circuit, and I look around and I say, wow, this view sucks. Okay, 1. And I take a step, and I'm like, wow, this view is really different. D, right? And I take another step, and then, and so on. Okay, so that is what f dot is. F dot is the view score, view scoring function. Okay. I know it's a little, childish, but I think it helps to understand the, all the players. I want to show that for all Borel functions, f dot from this to 1 through d, this is not a proper coloring. Okay? So in other words, there exists an x dot and exists an I in 1 through d, which are the paths, sorry, the edges, okay, such that f dot of x is equal to f dot of fi of x. Okay, so in other words, there's x here, and then there's fi of x here, and then they're in the same color. Maybe sorry, the same score, maybe 3 and 3. Right, that is. I prove that in fact this must happen, and therefore this is not a proper color, not a proper scoring of the views. Any questions about this? Okay. So this is precisely the statement. This is precisely the statement that I want to show. In fact, I will show an even stronger statement. That not only are these guys the same score, okay, so 3. In fact, the score must be equal to the edge that they traveled. So there's an I here, and the edge that you walked on was I. I call this I for obvious reasons. So in other words, I will actually show that for every Borel view scoring, there is I somewhere in there. Okay, there's I somewhere. And the reason I do this is because I actually, using this, I can go back to G. So I started at G, I went to G dot because G dot is the forest. And now I'm about to go back to G. Okay. Why am I allowed to do that? Okay, so I will just clean up that last thing. Claim, or maybe I keep using my word assertion. G circle, which has the cycles, has a Borel F circle, okay, star, from 1 to d that has no I. Okay. And therefore, if I can show that for all f from Vg, not the dots, but Vg, has I, then I will be able to show that every f dot has I as well. Okay. Then, for every f dot from Vg dot to 1 to d, I can define f to be f dot disjoint union f circle star, the special no I thing, okay, from G circle. And this theorem, or this thing, promises me that there is I somewhere. And it's not in here because I just said it wasn't in there. And so it has to be in here. Okay. So this is the part that allows me to go from G dot back to G. Any questions about this, dancing back and forth? Okay. We're in the final descent. Okay. So before, I proved a, I think impressive theorem using the black box of Lebesgue theorem. Okay. I didn't prove it, right? It's not boasting. I didn't prove it. But what is the magic tool that I use for this graph? Okay. What is the magic tool that I use? And in fact, I will use infinite games. So, a brief introduction to infinite games. If I have a subset of n to the n, which remember are just infinite sequences of natural numbers, this is called the payoff set. I can define a game, gamma of A, where I have two players, Alice and Bob, who each play one natural number, n0, n1, n2, n3, and so forth. In the end, they produce n0, n1, and so forth, which is an element of n to the n. And Alice wins if and only if this thing is in the payoff set A. So this is a well-defined game. You can play it with your friends. Okay. I'll define a strategy. Sigma is something that looks at what the board looks like at a certain time, and outputs a natural number. Okay. So a strategy would be, for instance, at this stage, I see these three numbers on the board, and the strategy cooks up some entry that I write down. That would be a strategy for Bob. Okay. And a winning strategy is a strategy in which there is something you can do, no matter what your opponent does, that will eventually produce a winning sequence. Okay? So if you just follow the strategy religiously, okay, then you are guaranteed to win. That is a winning strategy. And then here is the following amazing theorem by Martin, who was at UCLA. So this is the second, well, I guess first theorem. Martin called Borel determinacy. Determinacy. So this is a huge theorem, nuclear bomb of a theorem. And it says that if A subset of n to the n is Borel, in the sense that I described before, then the game gamma of A has a winning strat for exactly one of Alice and Bob, or Bob. Okay, yeah. No. In fact, this is a very long story about determinacy in set theory. This is one of the most fruitful sort of subfields of set theory. Okay, and I'll now define the following game. That will win us the story. So I have my deregular tree here. Okay. Here is the root. Okay. And Alice and Bob will play on this tree. Okay, this is the game board. Now you may be like, well, the game board previously was sequences of natural numbers, but I can just label all of the vertices of this tree by natural numbers. And so when you play a vertex, okay, or when you play on a vertex, that corresponds with playing a natural number. Do not worry about that aspect. Okay, so for all I in 1 through d, okay, and n in the natural numbers, I define a game, gamma and I, okay, where Alice and Bob take turns coloring the vertices of this tree. Okay. So Alice will be in charge of the top half. So this is Alice plays in this direction. Okay. And Bob will play in the other direction. Okay. A0, the first move of Alice, okay, will be to put a coloring on this dot. Okay. The next move by Bob will be to put a coloring on both of these dots. The next move of Alice will be to put a coloring on those two dots. And the next move of Bob will be put a coloring on these four. Okay. And so in this way, Alice and Bob build up a coloring of this entire tree. Any questions about the game? Okay. All right. Okay, so in this way, they produce a coloring of YD, okay, which was this tree, which, in fact, a specific view of this coloring, right, from the root here. Yes.
Is Baba taking like 2 turns in a row by coloring 2?
No. In each turn, they are coloring the thing indicated.
Oh, okay.
Yeah,
So this isn't exactly a.
Yeah,
copy of
but
the
you can
original.
encode this
Sure. Okay.
in this.
Yeah. Okay. Got it.
Also, unfortunately, I don't have time to go over that. So, but each move, they fill in one of these bubbles. Okay, I should really say that this bubble is this. Okay. So first move, Alice fills in this one. Second move, Bob fills in these 2, and so forth. Okay. Any questions about this fun game? The winning conditions are Alice wins if f dot of x, sorry, f, where I fixed a Borel coloring, Borel view score, f, if this guy is not equal to I, where I is this parameter in the game. And Bob wins if f of x is equal to I. Okay. So we color in this whole thing, and in the end, the judge standing at the root will look around and score this view. And if the judge says, that's a I, then Bob will win. And if the judge says, nah, that's not an I, then Alice will win. So hopefully this game makes sense. I'll now make one claim, apply the pigeonhole principle once, and then achieve victory. So the first claim is the following. Okay, by the way, because I assumed f was a Borel function, I can determine if x is in this, will lead to this outcome or will lead to this outcome. Okay. And so in fact, this is a Borel game. The payoff set is Borel. This is a Borel condition. And so by this nuclear bomb theorem of Borel determinacy, this game is determined. There is in fact a winning strategy for either Alice or Bob. And this is very important. For all n, which is the color of the root, okay, I get d different games, gamma 1n through gamma dn, right, which just corresponds to the winning outcome. Okay. And also, I forgot to mention, this edge has to be I. That is the axis along which the game is played. Okay. The claim is that for one of these games, Bob can force a win. In other words, he has a winning strategy. Please also note that Alice's job is much easier than Bob's, okay? Because Alice just needs to avoid one thing, whereas Bob wants to target one thing. Okay. So Bob definitely has it worse in this game. However, in one of these games, or at least one of these D games, Bob can indeed force a win. I'll prove this for you. Proof. Suppose not, for sake of contradiction. Okay. Then I'll do the following. So I place the color n on the root, and let me arrange the game board in this way. Okay. I will have D Alices playing against each other. Okay. So I'll have Alice number 1 playing in this direction. Okay. So Alice number 1 will play in this direction. Okay. Alice number 2 will play in this direction. Okay. And Alice number 3 will play in this direction. And now let us analyze the game from each of their perspectives. So before any of them, and they will play simultaneously. So before any of them have done anything, okay, right now it's just the starting position of this game. Okay. Yes?
There's also 3 Bobs.
There are no Bobs.
No.
There are no Bobs. But Bob is about to show up in an imaginary way. Okay, so right now they just see one node, which is the root, which has been colored n. Okay, and so they color in their vertex, right? That is the first move of Alice, right? Alice always gets to color in the first. Right? So all three Alices color in this one, and this one simultaneously. Now, what does it look like from Alice 1's perspective? Alice sees these two things that have been colored now. So it looks as if Bob has made a move. So in her mind, Bob 1 has just played, when in fact it was just these two Alices. Okay? So imaginary Bob 1 has played here, and so Alice will play here. And in fact, all three Alices will make the same conclusion, and so all 6 of these things will now be colored. But then each Alice will think, Bob has made his second move, and then they will continue in this way. And now the contradiction is as follows. Each Alice has a winning strat. Okay. And so they can just fill out this thing following the strategy, playing against the imaginary Bob in their head. Okay. And in fact, I get something which is not colored I for any I from 1 to D. There's the contradiction. Okay. And so in fact, this cannot happen. Okay. All the Alices cannot simultaneously have a winning strategy. And so by Borel determinacy, it must be that one game, Bob has a winning strategy. Okay, any questions? Okay. We're almost there, Okay. Now, I will play, I'll apply the pigeonhole principle once. Okay. Notice that here it's for every n, right? So by the pigeonhole principle, there exists an n such that there are two i's, I0 different from I1, such that Bob can win. Sorry, the other way around. My bad. There exists an I, and n0 different from n1, such that Bob wins both gamma n I0 and gamma n I1. Right? This is because there are infinitely many here, but only finitely many numbers up here. Yeah.
Do you mean gamma m0i and gamma m1i?
Yeah, of course. I'm just mixing up my letters at the very end. So sad. Okay. And in fact, the pigeonhole principle works equally well if I had replaced n by d plus 1. In other words, I consider colorings from this y to just 1 through d plus 1 instead. Okay. So in fact, I did not even need to work with countable colors the entire way. But that's just a parenthetical. And here is the finality. Okay. I'll draw the game board in this way. This is colored n0, this is colored n1. Okay. And now I will have two Bobs playing against each other. Right? Everything is balanced in the world. Here I have an Alice tournament, and now I have a Bob tournament. Okay. And Bob 0 will be rooted here. Okay. And Bob 1 will be rooted here. How does it look from Bob 0's point of view? He is at a root, and this node has already been played. So in his mind, an imaginary Alice has played the first move of the game already. Okay. So he will color these two in his move. But of course, Bob 1 has the same conclusion. So Bob 1 will color these two. And exactly the same thing happens. Okay. Each Bob imagines they're playing against an Alice, and they fill out this tree together. Okay. And so what is the conclusion? The two Bobs produce a coloring of this tree Y. Okay. But and Bob is winning. Bob is winning. Bob wins. Each Bob wins because they're playing the game in which they win. And so in the end, this color, sorry, this view, from Bob's point of view, will be scored I. But this view, from this Bob, will also be scored I. And so I have I. That's the end.